Chapter 13, Lesson 2. In this lesson we'll take a look at some ways to express concentration. And qualitatively we can just say the substance is either dilute or concentrated, but it's more important to be able to tell how dilute or concentrated it is quantitatively. So we'll take a look at these 5 ways of expressing concentration. Now 2 of these we've actually already seen. We've seen molarity, and we've done some calculations with molarity in Chapter 4. And then we've also seen mole fraction. We've done some calculations with mole fraction in Chapter 10. So 2 of these will be familiar, and the rest we'll take a look at in more detail. The first then is something called mass percentage. And mass percentage essentially is what it sounds like. It's the percent of mass of your substance dissolved in the total mass of solution. So you take mass of part divided by mass of whole, and then percent means per 100. The word cent actually means 100, so then we multiply by 100 to get a percentage. The second one is similar, and it's something called parts per million and parts per billion. Now this is very similar to percent. Technically percentage was parts per 100, but very often when we have a very small amount of solute in our solvent, for example drinking water has a tiny amount, say, of heavy metals, say mercury in it. So oftentimes that's expressed in parts per million. And essentially the equation is you take again the mass of your solute divided by the total mass, and then you multiply not by 100 but by a million. Remember, 10 to the 6th is actually 1 million. So it's essentially the same thing as percent, but you multiply by a million. With parts per billion, it's exactly the same thing, except you multiply by a billion in the end. So in all 3 of these cases, it's actually a part divided by whole times whatever you're talking about. You can even say parts per 1,000, parts per trillion, even those can also come up. And just remember, this is by mass. So why don't we do a quick example of this. So we have 2.5 gram sample of groundwater was found to contain 5.4, this is micrograms, a millionth of a gram of zinc 2+. What is the concentration of zinc 2+ in parts per million? So our idea is parts per million. Essentially it's mass of your zinc 2+ divided by total mass multiplied by 10 to the 6th, or a million is the idea. Now the only thing we have to do here is ensure that both the top and the bottom of the equation are in the same unit. So we can either convert both to grams, or we can convert both to micrograms. So why don't we convert both to micrograms, since zinc 2+ is already in micrograms. So all we have to do here for the top is you've got 5.4 micrograms, and we can divide that by the total, which is 2.5 grams. So we'll have to convert 2.5 grams into micrograms. And a microgram, 1 gram, is 10 to the 6th micrograms, or a million micrograms. So really we can just put 2.5 times 10 to the 6th micrograms, and we can solve it. Alternatively, you could have converted micrograms into grams. You could have also said you got 5.4 times 10 to the negative 6 grams over 2.5 grams, and this would have done the same way, the same thing. We just then have to multiply by 10 to the 6th, or a million. So in both these cases, what happens is, this is actually a pretty simple example. The 10 to the 6th, if you do this correctly, will actually cancel out both on top and the bottom, and you just end up dividing 5.4 by 2.5. And you get yourself, in both cases, 2.16 part per million. So pretty simple problem. You can also, if you want to try this version, if you multiply this, if you divide these two numbers, you should get the same amount. and that should work. You should also get 2.16 parts per million. Alright, let's take a look at the last few. Mole fraction, which we've seen in chapter 10, is very similar to this idea of percent or parts per million, except it's not in terms of mass, but in terms of moles. So you take the moles of your solute divided by total moles on the bottom. And sometimes we use this. Actually, there's a special application, as we'll see later on, for this. Anytime you need mole fraction of a solvent. So you could, for example, put moles of your solvent on top, as well as moles of solute. And as you'll see, there's an application of this later on. In the gas chapter, we did solute. In other words, what you have less of went on top. But we can reverse it. We can put what you have more of, which is the solvent, on top, and then divide by total. Molarity we've seen, so in chapter 4, so we won't probably spend too much time. The only thing we'll say here is, since molarity is moles of solute per liter of solution, because we're dealing with liters, anytime you heat up a solution, its volume expands. Warm water actually takes up a little more space than cold water. So the problem with using molarity is if you have a reaction in which the temperature goes up, then your volume throughout your reaction changes. The volume goes up, and then your molarity goes down. So your molarity changes throughout the reaction, which is not a good thing. So molarity is what we call temperature dependent, and sometimes this doesn't pose a problem, but oftentimes it does. So because of this, because of the fact that molarity is temperature dependent, we have come up with another way of expressing almost the same thing, and this is called molality. It's very similar to molarity, and logically, but it's molality, and it's designated with a small cursive m. Molality is mole of solute, just like in molarity, but divided by kilograms, not liters, but kilograms, and then not solution, but solvent. So both of these are actually different for molality than they were for molarity. So this is actually an important difference that we'll have to take a close look at. So because you have kilograms on the bottom, if you heat up water, the amount of kilograms in there does not change. The volume changes, the kilograms does not change, so this is not temperature dependent. It is temperature independent, and this will suit some of our applications a little better than molarity. Now, we can actually go from molarity to molality. The only thing we'll have to know is density. So you can go between molarity and molality, and then back over through density, because recall molarity is liters on the bottom, molality is kilograms on the bottom, and what relates mass and volume is density. Recall that density is mass over volume, and it's the idea. We'll see an application of this in just a second. In fact, here it is. We have actually two problems here. So in A, we're saying we have a solution of hydrochloric acid, HCl, which contains 36% HCl by mass. First, we want to calculate the mole fraction of HCl, and then we want to calculate the molality of HCl. So let's take this one at a time. Let's go ahead and do the mass percent to mole fraction. Now, mass percent, 36%, essentially means that you have 36 grams of HCl in 100 grams of total solution. Because remember, mass percent is per grams total. What this means is 36 of the grams are HCl, the rest of the grams are actually water. So in this 100 you get 36 grams of HCl, and then you have the remaining, which in this case is 64 grams of H2O. And this will be important in order for us to then go into mole fraction. In fact, that's exactly what we need to do. In order to get the mole fraction, we have to convert both of these into moles, from grams to moles. So why don't we do that? Why don't we convert 36 grams of HCl into moles, and recall that a mole is just the mass from the periodic table. In the case of HCl, we got 36.46 grams per mole. A mole, and we can get that calculated. We can do 36 divided by 36.46, so we'll get very close to 1, just a little less than 1. So 36 divided by 36.46 gives you 0.987. Let's do 4. Let's go and keep 4 significant figures. Moles of HCl. If we do the same thing to water, we got ourselves 64 grams of H2O. A mole of water is exactly 18.02 grams. So 64 divided by 1802 gives us 3.552 moles of water. And now we can get our mole fraction. Now we want the mole fraction of HCl. So X mole fraction of HCl will equal, we'll have to put moles of HCl divided by total moles. So our moles of HCl is 0.9874, and on the bottom we'll put total moles, which is 0.9874 plus 3.552. This gives us, if you do the calculation, we can do the bottom one first, and 0.9874. So we got essentially 0.9874 over 4.539 for the total, and we get ourselves 0.9874 divided by 4.539. That gets us 0.2, because we have 2 sig figs, 0.22 for our mole fraction. This is our final answer, essentially. Now, mole fraction is actually a unitless concentration expression. So this is really one of the rare cases in which there is no unit. The unit is missing. That's because we're dividing moles by moles. This was moles, and so was this. So both the moles cancel out. We have a unitless expression. So this happens rarely, but it does happen. So now, why don't we go into molality? And to calculate molality, let's go ahead and retain these two values, 0.9874 and 3.552. Recall that molality is moles of solute divided by kilograms of solvent. So in our case, our moles of solute is this value. This is our solute, as this is what we're dissolving, and our solvent then will be the water. And we essentially have, I'll go ahead and highlight this with a different color, we have 64 grams of our solvent, because water is our solvent. So here really are our two numbers that we have to worry about. This is our solute, and there is our solvent. So really it's a matter of dividing these two by each other. The only thing is this has to be in kilograms. So it is getting quite crowded. So let me take care of this and we'll go on to the next page to be able to solve it. So then the molality of our solution is moles of HCl divided by kilograms of water. In this case, our moles of HCl is 0.9874, and we had 64 grams of water, so 64 grams converted into kilograms is actually 0.064 kilograms, divided by 1,000, or undo the decimal place 3 times to the left, to make sure you do it to the left, not to the right. So we can divide this by 0.064, and our molality then comes out to be 0.9874 or 0.064. We get ourselves 15.4. In fact, since we had two significant figures, we'll have to say 15, and you can put a little cursive M, or you can say 15 moles per kilogram. One of these two ways will work. Molality will very often be similar to the molarity. So if you were to calculate the molarity, for example, you'd probably get in the order of 12 or something. I think the molarity of this is actually, if you were to convert this to molarity, the molarity would actually be 12 molar. So molality and molarity will be roughly on the similar amounts. But this is how you get molality. And this, I believe, concludes for us lesson 2 of Chapter 13. Thank you for enjoying it.